Shown here is a piston cylinder arrangement. The cylinder contains a finite number of molecules of a gas. The cylinder is also fitted with a knob opening on its wall to allow addition and removal of the gas. The piston exerts a constant pressure P on the gas that is within the cylinder. If the gas in the cylinder is heated by an external source of energy, the temperature of the gas increases, and the molecules become more energetic and push the piston upwards. The doubling of the volume of the gas due to the doubling of its absolute temperature is an indication that the volume of the gas is directly proportional to its temperature. Now if the pressure that is acting on the piston doubles, while keeping the temperature constant, the volume of the gas within the cylinder is halved. This shows that the volume of the gas is inversely proportional to its pressure. Finally, half of the molecules of the gas are allowed to escape out of the cylinder by opening the knob on the cylinder wall, until half the mass of gas within the cylinder is gone, while the temperature of the gas and the pressure exerted by the piston are both kept constant. The remaining gas molecules occupy a lesser volume, resulting in the piston moving downwards. The reduction in volume, due to a decreased number of molecules, indicates that the volume is directly proportional to the number of gas molecules. Combining the three relations that we just obtained into one, we get that the volume of the gas is proportional to the number of gas molecules times the temperature divided by the pressure. This last relationship is called the ideal gas law. 1 mole of any substance contains 6.02 to 14199 times 10 to the power 23 molecules of that substance. The number 6.02 to 14199 times 10 to the power 23 is called Avogadro's number, written as capital N, followed by subscript capital A. Therefore, 1 mole of a substance contains a number of molecules equal to Avogadro's number. For example, 1 mole of dinitrogen, or N2, contains 6.02 to 14199 times 10 to the power 23 molecules of N2, and 1 mole of carbon contains 6.02 to 14199 times 10 to the power 23 carbon atoms. The unit of mole is written as mol without the e at the end. The kilomole is equal to 1000 moles. The molar mass of a substance is the mass of 1 mole of that substance. The molar mass has units of kilograms per mole, and is expressed by the symbol capital M. The molar mass of a substance is equal to Avogadro's number times the mass of 1 molecule of that substance. The number of moles in a sample of a specific substance is equal to the number of molecules in that sample, divided by Avogadro's number. This is also equal to the mass of that sample in kilograms, divided by the molar mass of the substance in kilograms per mole. As we have seen before, the volume of a given sample of an ideal gas is proportional to the number of gas molecules in the sample times the temperature divided by the pressure. Since the number of molecules is related to the number of moles by the constant Avogadro's number, we can replace the number of molecules in the previous relation by the number of moles, without changing the implied proportional relationship. Finally, we can change the proportionality relation to an equation by introducing the universal gas constant, which is written as capital R, subscript U. This equation is usually written as the pressure times the volume is equal to the number of moles times the universal gas constant times the temperature, and it is known as the ideal gas equation. To determine the SI units of the universal gas constant, let's rearrange the terms of this equation so that we have RU is equal to the pressure in pascals times the volume in meters cubed over the number of moles times the temperature in Kelvin. Pascals can be replaced by newtons per meter squared, and then multiplying by meters cubed, we get Newton meters, which is joules. And so, Ru has SI units of joules per mole Kelvin. In fact, the universal gas constant has a value of 8.315 joules per mole Kelvin. The universal gas constant is the same for all gases that obey the ideal gas law. The gas that obeys the ideal gas equation is referred to as an ideal gas. In the last slide, we introduced the ideal gas equation. An alternative form of the ideal gas equation can be obtained by multiplying the right-hand side by the molar mass, divided by the molar mass, and then regrouping the terms. The molar mass times the number of moles is equal to the mass in kilograms, and the universal gas constant divided by the molar mass is equal to the gas constant for the particular gas in question. The gas constant for any particular gas has units of joules per kilogram Kelvin. Thus we have pressure times volume is equal to the mass times the gas constant times the temperature. Finally, the terms of the ideal gas equation can be rearranged by moving the volume to the right-hand side. Then we can replace mass over volume by the density, ρ, in kilograms per meter cubed. Thus the alternative form of the ideal gas equation is written as, the pressure in pascals is equal to the density in kilograms per meter cubed, times the gas constant for the particular gas in question, times the temperature in Kelvin. It should be noted that the universal gas constant is the same for all gases, while the gas constant is different for different gases, depending on the molar mass of the gas. There are two types of specific volume: molar specific, which we write as V subscript, uppercase M, and mass specific, which we write as V subscript, lowercase m. The molar specific volume is equal to the sample's volume in meters cubed, divided by the number of moles in the sample. The molar specific volume therefore has units of meters cubed per mole. The mass specific volume is equal to the sample's volume in meters cubed, divided by the sample's mass in kilograms. Therefore the mass specific volume has units of meters cubed per kilogram. It is clear from the definition of the mass specific volume that it is also equal to 1 divided by the density in kilograms per meter cubed. Next we can rewrite the ideal gas equations in terms of these specific volumes. The ideal gas equation can be rewritten in terms of the molar specific volume by dividing the left-hand side by the number of moles, and then replacing V over N by the molar specific volume. To get the pressure times the molar specific volume is equal to the universal gas constant times the absolute temperature. Similarly, the alternative form of the ideal gas equation can be written in terms of the mass specific volume by dividing the left-hand side by the mass, and replacing V over M by the mass specific volume. To get the pressure times the mass specific volume is equal to the particular gas constant times the absolute temperature.